Hello friends, in this lecture I will focus on Programmable Logic Device, also known as PLDs, and these PLDs are nothing but Programmable IC. So it is nothing but Programmable IC, and that can be used to design circuit as per our requirement, and it is programmable, so we can design the circuit. Like if I want to design it as adder, I will use it as adder. Again, if I want to use it at subtractor, I can use it at subtractor also. Later, if I want to use at mux, we can use as mux, demux, whatever. So we can use these PLDs as per our requirement. And the basic structure of the PLD is AND array followed by OR array. So this is the basic structure. First we will have AND array and then OR array will be there. And here the word programmable is used. So there is something that is programmable, and depending on this programming we have three categories of PLDs. First one is ROM, second one is PAL, and third one is PLA. So ROM is nothing but read only memory, and you may also use PROM. We can call it PROM also. So programmable read only memory. PAL is nothing but programmable array logic. PLA has full form programmable logic array. Now the thing which is programmable is, for read only memory we have OR structure which is programmable. For PAL AND is programmable, and for PLA both AND as well as OR is programmable. Now there is a trick to remember which part is programmable for which PLD. So ROM, PAL, PLA, they are example of PLDs. Now which part will be programmable? You can remember it like this. See, ROM has the word OR. Since OR word is there, so we will say OR is programmable. In PAL it is programmable array logic, so you can remember it like this: programmable AND. Okay, programmable AND. So AND gate is programmable. PLA, so here it is programmable logic, you can say programmable logic. And since logic is programmable, so AND as well as OR both are programmable. Okay, and remember, this is not, the full form is not programmable and logic. Full form is programmable array logic. The trick I told you is for remembering which part is programmable, which part is fixed. Okay, now the basic structure that we will have, like when I say programmable, so how to show these programmable connections? We will show programmable connection like this array or this mesh. Here suppose we have three signals I1, I2, I3, and initially here AND gate is there. So initially this AND gate has all the inputs. Similarly, I am using second AND gate here. So this second AND gate is also having all the input connected to it. So the connection is represented by this cross, and this cross represent, it is programmable connection. It is programmable connection. So initially all the inputs are connected to this AND gate, and it can be shown like this. So see here, this line I1 is input, I2, I3 is input. This gate 1, it is connected to I1, I2, I3. Here also if you see I1, I2, I3, they are connected through this fuse. We call this fuse. So they are connected through this fuse. Now how to use this array to design any circuit? For that, suppose I want to, and see, this is the same structure, right? The initial one, this is the same structure as the initial one. Suppose I want to design two function where function f1 is I2 into I3 and function f2 is I1 into I3. Now if you see here, function f1 has I2 and I3 as input. So what we will do, we will remove this connection I1 from f1, and let me write this. Suppose here I will have f1, here we will have f2. Similarly, this is the analogous circuit. In exam or if somewhere they ask, there is no need to draw this thing. You can write this form only to design. Now f1 is nothing but I2 and I3, so I1 is not there. So what we will do, we can remove this connection I1. Okay, we will remove this connection I1. So if you see here, what is f1? F1 is I2 into I3. And if you want to see here, what we will do, we will remove this fuse. Okay, so it is I2 into I3. Similarly, f2 is I1 I3. So I1 I3 means what I should remove? I should remove this I2, right? So here I am removing I2. Now what is my f2? My f2 is nothing but I1 I3, right? And so what is happening here is, it is like I am removing this connection. And this process of removing unwanted connections is known as firing of the circuit or burning the circuit. Okay, we will remove unwanted connection through coding or through programming. And once, if I want to reset it, what we will do, we will reset it. And resetting means all the connections will be again there. Okay, resetting means that. So this is how we will use. Now after resetting, if I want to change, if I want my f1 to be, suppose if I want my f1 to be I2, okay, it is I2 I3 initially, right? Now I want it to be I1 I2. Then what we will do here, we will keep I1, we will keep I2, but we will remove this connection I3, and F2 is suppose I1 I3 only. So this is like this, right? And so this is now I1 I2, right? So this is how we do the connection to get output. Now I am going to use PROM or ROM, that is read only memory, to design some circuit as PLD. Okay, so I am going to use ROM as PLD, and as you know, this ROM is nothing but fixed and followed by programmable OR. So this fixed and it can be represented by a decoder only. Okay, so instead of fixed and we can use decoder also. And why I am saying so, you can see from this example. Suppose I want to implement function FAB, which is nothing but summation M23. So it is summation M23 means it is a standard SOP form, and this summation M23 is nothing but M2 plus M3, right? Min term 2 plus min term 3. So min term 2 means 2 is nothing but 10 in decimal equivalent, 3 is 11 in decimal equivalent. So it is nothing but, see, inputs are A, B in order. So it is nothing but A, B dash or A, B bar plus A, B, because it is 1 0 1 1. Okay, so 0 means B bar, 1 means A, and similarly 1 1 means A, B. Now here you have to notice one thing that we call input buffer. So this structure is known as input buffer, and it takes input as A and return output A and A bar. So this input buffer is nothing but this thing only. So A is there and one signal passed, the same signal passed through NOT gate giving A bar. So just remember this structure we will use now onward. So this is input buffer that returns A bar if input is A. Now coming back to my question, I want to implement AB bar plus AB. I want to implement this equation, right? So let me see how to implement this. Okay, so see here, I'm using that buffer as I told. So A is there, and see what I want to implement. I want to implement AB dash plus AB. Okay, wait, it is AB dash. Yes, M2 is AB dash, right? So M2 plus M3. Fine. So AB dash. This is wrong. Let me remove this. I will connect that later. Okay. So AB dash plus AB. M2 plus M3. Now here see. I am using two input buffer. One for A, one for B. So from here I will have output as A and A bar. Output as A bar, and from here I am having output as B bar, right? Now here I am using two AND gate, first AND gate, second AND gate. Now see, from here what I want from here A B bar. So I connect A here and B bar here. If you see, A and B is connected, so I am getting AB from here. Now I want these things, right, through OR gate. So output I want is AB bar plus AB. So AB bar comes from here, AB comes from here, and I will get this output. So this structure that I use here, the structure that I use here, wait, not this one, the structure that I use here, this whole structure can be replaced by this simple 2x4 decoder. And you know decoder is what? Decoder, if it takes input n input, decoder takes n input and returns 2 raised to power n output. Okay, and this 2 raised to power n output is nothing but all possible mean terms. And if you see here, this AB dash, AB, they are nothing but standard mean terms. Fine. So if it will take input as AB, it will return mean term 0, mean term 1, mean term 2, mean term 3. So mean term 0 means it is nothing but AB, A dash, B dash. Mean term 1 is nothing but A dash, B. Mean term 2 is nothing but A, B dash. Mean term 3 is nothing but AB. Fine. So these lines are representing the mean terms corresponding to this input signals. Okay, now what I want, so now I want my output to be AB dash plus AB. So see, this whole line is AB dash. So from here I will take one signal plus AB. So from here I will take plus AB. So what is my output? Now my output is AB dash plus AB. Okay, so this is the way that we will use to implement any function using ROM, that is fixed and. This decoder is representing fixed and, okay, followed by OR gate. Okay, so this is nothing but fixed and followed by programmable, or this is OR gate. Fine. Now I will see an example to explain in a better way. So the question, suppose the example is this: implement the following boolean expression using PROM. In exam they may ask ROM also. Okay, so functions are f1 abcd equals to summation m1 2 4, these mean terms are given. F2 abcd is something like this. Now here if you see, these are not standard mean term. Standard mean term must have all the input variables, and here input variables are a b c d, but here d is not here, d is not there, and in this also d is not there. Okay, so what we will do is, in step 1 we will write the given expression in standard SOP form, and to write in standard SOP form we need standard mean term. Okay, so if you see here, this f1 function is given in standard SOP form because these are standard mean term. 3 5 means a dash b c dash d, right? So these are standard mean term, but this function f2 is not standard mean term, like not standard SOP, because mean term are not standard. So what we will do, first we will convert this function f2 in standard SOP form. For that we need to write standard mean terms, required standard mean terms. Okay, so that is the first step. Remember to use ROM as PLD. Okay, so just remember this, to use ROM as PLD we must have standard SOP form, must have standard SOP form. And if standard SOP form is not there, we will write function in standard SOP form, and we can do so. So here I have shown how to do so. Okay, so f2 is given like this: a dash b dash c dash plus a dash b c d dash plus a b dash c dash, right? Now this a dash b dash c dash, it can be written like a dash b dash c dash into 1, and this can also be written like a b dash c dash into 1. Now this 1 is nothing but, like, it, this 1 can be written like, because d is missing, right? Since d is missing, so we will write this 1 as d plus d dash, and here also d is only missing, so we will write this 1 as d plus d dash. So what I am doing, a dash b dash c dash multiplied by d plus d dash, and what this d plus d dash is representing, it is representing 1. Similarly this has standard, this is standard mean term, so no need to change it. Here if you see, it is a b dash c dash d plus d dash, so it is also now standard, because one I use this 1 as d plus d dash. So now we will expand it. After expansion we will have a dash b dash c dash d plus a dash b dash c dash d dash plus this term plus these two terms, right? A b dash c dash d plus a b dash c dash d dash. Now we will write it in terms of mean term. So if we want to write in terms of mean term, then what is this? A dash b dash c dash d means it is 0 0 0 1, right? A dash b dash c dash d dash means 0 0 0 0. Similarly it is 0 1 1 0. Here it is 1 0 0 1. This one is 1 0 0 0, right? So I wrote those things here, and then I wrote their decimal equivalent. And why I wrote their decimal equivalent? So that I can write those things. Okay, so here I will have the standard mean term. Fine, summation m 0 1 3 5 8. Now here we have total 4 variables, input variables. If you see a b c d, so number of mean terms will be 16. That means here we need 4 cross 16 decoder as fixed gate, right? As fixed AND gate. So I draw that a b c d, and 4 cross 16 decoder is used, and these are the mean terms line, right? This will be the output from the decoder. 0 1 2 3, these are corresponding mean terms, right? So if suppose d naught is mean term 0, so it is nothing but a dash b dash c dash d dash, like that. Similarly d6 is nothing but a dash b c d dash, likewise only, right? Now let me see what are the equation that I want. So the equation that I want is, this is function f1 and this is function f2. Now remember one thing, while solving any problem related to PLD, See number of output functions. If number of output function is 1, then number of OR gates required will be 1. If number of output function is 2, number of OR gate required will be 2. If number of output function is 3, number of OR gate required will be 3. That means number of output function will decide number of OR gate. Okay, so number of output function decide number of OR gate. Here we have two output function, F1 and F2. So number of OR gate required will be 2. So I am drawing this two OR gates here. Okay, so two OR gate will be required. So here is two OR gate. Then I will make a straight line like this, and drawing a line like this means they are not connected now. So now these lines are there. Okay, we will draw two lines. Now these are the things and they are not connected. Now to get F1, suppose from here I will have F1, from here I will have F2. Now to get F1, what are the mean terms that I need? I need 1, 2, 4, 5, 6, 8, 10 and 12, 14. Okay, so where is line 1? Here. So I will make this connection, M1, M2, then comes 4, 5, 6, 8, 10, 12 and 14. So this gives you F1. Similarly for F2, what I want? 0, 1, then line mean term 3, mean term 5 and mean term 8. So this will give you F2. In this way I can design my required Boolean function using ROM. Okay, so inputs are A, B, C, D. Inputs are A, B, C, D and outputs are F1, F2, right? So this is how we can use ROM as PLD to design or to implement any given function. Okay, so see, if you see here inside this box, whatever is this, so input is ABCD, output is F1, F2, and inside is ROM as PLD. So this is all about basics of PLDs and how to use ROM or PROM as PLD. In next lecture I will focus on PAL, that is Programmable Array Logic, and it is PAL, Programmable Array Logic, and after P I am getting A, so it is the logic array where AND is programmable or is fixed. Okay, if you have any doubt, feel free to ask me. Thank you.